topology in these quantum fields. Now the problem is to understand all that stuff, what I've just said, but it is high level. It's sort of like PhD 2 level, right? And so that's the problem. And one of the aims of this whole lecture series of deGarisMPC is to teach you to this high level, because once TQC comes, once quantum computers are scalable, then, well, as I was saying before, everything changes. So then you can imagine that ministers of science policy or commerce or whatever, picking up the telephone and calling the presidents of major universities and say, your university must teach TQC, topological quantum computing. It's important for the economy and the country, okay? So the president then calls in his deans of computer science, physics, mathematics, and so on, and says to them, I've just had a phone call from the minister of whatever, and I've been instructed to tell you, deans, that this university from now on will have to teach TQC. So, okay, go to it. Well, then the deans go back to their offices and start looking into the nitty-gritty of what's involved in teaching this stuff that's so revolutionary for the future economies of their countries. I mean, they understand, well, once they educate themselves a bit more, but they will be shocked at the level of PhD 2 level of the math, the pure math, and the theoretical physics needed to understand this stuff. Now, let me give you a little bit of history so to see where all this came from. Go back 80s, I guess. One of the smartest guys in the world, in a sense today's Einstein, is a guy called Ed Witten, W-I-T-T-E-N, Ed Witten. Now, he is the only guy to have won the prestigious Fields Medal. It's sort of the equivalent of the Nobel Prize in mathematics, but Nobel, the guy who started his prizes over a century ago, it seems he just was not very interested in mathematics, so he did not include mathematics in his prizes. Now, recently, as from 2003, I think, the Norwegian government has created the equivalent of a Nobel Prize in mathematics, and it's been won every year, so for the last 9 years or so. But the general population has not heard about it much yet. The name of the prize is Abel, A-B-E-L, the Abel Prize. So, because pure mathematics is not a topic of a great favourite for the vast majority of people, because it's so difficult, right? It's too abstract for 99.99 whatever % of the population. So it probably will remain somewhat unpopular. But anyway, the Fields Medal was the equivalent. It's awarded every 4 years, and to people under 40 years old. So in that sense, it's ageist, and I'll talk a bit about that a bit later. And more difficult to get because it's every 4 years. So Ed Witten was one of the people who got one. He won it in pure mathematics, but he's a physicist. He's a mathematical physicist. His specialty is field theory, quantum field theory. And what he did was, he's looking into the highest reaches of his subject. And what he did effectively was bring together three-dimensional topology, and quantum field theory, or topological quantum field theory. And he then created techniques that simplified the work of topologists, pure mathematicians, to such an extent that they cleared up their field the work that had taken about a decade previously, they were then able to redo far more simply in a matter of weeks, literally. So it revolutionized their field. And as a result, Ed Witten got the Fields Medal for that major contribution, even though he's not really, strictly speaking, a pure mathematician. But to understand what he did and related work, you need to reach a very high level. So it's PhD 2 level. So one of the aims, my ambitions, is to take you to that level. If you're interested, you could follow PhD 2 level courses in topological quantum field theory, TQFT, and low dimensional topology and so forth. That's one of my aims. It's one of the it's something I really want to master. It's part of it. Okay, so TQC. Now another one of my research interests is what I call X-TECs. You've probably heard of nanotechnology. That's molecular scale engineering. So you can put atoms where you want. It's a kind of mechanical chemistry. Now, humanity does not quite yet have that capability to do that. To pick up one atom from one place and put it somewhere else. We're not quite there yet, but nanotechnology is advancing at a great old rate. So what does that mean? Nano is just short for a billionth of, in this case, a meter. So a billionth of a meter is at the scale of molecules. So nanotech is the engineering at the molecular scale. So you're making these tiny little machines from molecules. You're making molecular machines. Okay, so that's probably well known to you, nanotech. Well, one of my interests is something called femtotech. Now, femto is a level 1,000,000 times smaller. It's down at the level of quarks and gluons inside protons and neutrons and so forth, inside the nucleus. So hugely smaller. Now, a couple of months back, I figured out a way how to compute. Remember, my background was computer science. So I figured out a way, in principle, to compute using the properties of quarks and gluons. A proton or a neutron has 3 quarks, and they're held together by gluons. That's why they're called gluons, because they glue, or hold together in a sense, the quarks. Okay. So potentially, if you could have huge numbers of these in a really tiny space, a femtotech could outperform a nanotech by a factor of 1 trillion. Just hugely more performant. So one of the reasons why I want to do all this MPC stuff is to give myself more knowledge so I can more effectively theorize, speculate about the possibility of lower level, tinier scale technologies. Now, if you go down another scale of 1,000, 1,000 times smaller than femto, you get to atto, A-T-T-O, atto. So could there be an attotech? Well, using the weak force, there are particles in the weak force in physics that allow me, again, in principle, to find a way to compute using those properties. So potentially an attotech. Now, every time you go down a factor of 1,000 in scale, in size, your potential performance increase compared to the scale 1,000 times larger increases by 1,000 to the 4th power. So that's 1 trillion times, 1 trillion times more performant. So I call this term X-TECs. Now, X refers to the label of a particular scale level, like nano. Pico, like picotech. Pico is 10 to the minus 12 of a meter. Femto, 10 to the minus 15 of a meter. Atto, 10 to the minus 18. And the next one is called zepto, Z-E-P-T-O, zepto. That's 10 to the minus 21 of a meter, and so on. So in theory, maybe you could go all the way down, and the smallest scale that humanity knows of at the moment is the so-called Planck, P-L-A-N-C-K, Planck, the famous Planck. The father of quantum physics. So at the Planck scale, which is 10 to power minus 35 of a meter, So almost a trillionth of a trillionth of a trillionth of a meter, incredibly small. Maybe it might be possible to have a kind of plank tech. So that's one of my dreams, is to dream up some kind of plank tech. So it's one of my research interests. Okay, so X-techs. All right, now there are other, well, connected with X-techs is a concept I call SIPI, S-I-P-I, that's search for